Okay, good day. I hope you enjoyed these slides. I'm going to be talking about energy and units. One thing that we have to remember that the units will have to be defined in based on um, work. As we mentioned in class, energy is the capacity to do work. So this is what we're going to be doing. So let us think a little bit in terms of what we have been doing before. In physics, as I mentioned in class, the kinetic energy can be said as being directly proportional to the mass and the velocity of the moving object. So, for instance, if you have a car and a truck moving at the same speed on the freeway, let's say 55 miles an hour, even though they are going at the same speed, the kinetic energy involved, the amount of energy that they use to get to that speed, is larger in the truck, the heavier truck. And the proportion that we have here for the kinetic energy, and I am using two letters to express kinetic energy, this is one thing, is related to this formula: one half of the mass of the object times the square of the velocity. This is a physical entity that I'm not going to get into the how do we get to this one half. In fact, there is a joke here saying when this guy was falling from a big building, and as he was going to hit the ground, he said something about, I'm so glad that the kinetic energy is only one half of the mass times the square of the velocity. Anyways, so when the mass is in kilograms and the velocity is in meters per second, the unit for kinetic energy becomes kilogram meter squares over second squared. And the reason that we use kilograms is because the Newton, which is the unit for force, is based on kilograms, and this is mainly coming from the physicist point of view. Now, if we think about the work being represented by pushing something, so 1 Newton would be 1 kilogram per meter over second square. If you multiply that by 1 meter, then you will have kilogram meter square over second square. That would be 1 Newton per meter, and then that would be the unit that we will be using here, and we will call that the joule. And capital letter J would be the joule given as this. Now, just to give you an example of how much energy that is, if you have light bulb, for instance, running for about 1 hour, you are using about 3.6 10 to the 5th joules. Now, notice here that we have also kilowatt hour. And this is because it has been common practice not to measure energy but power. And power is the amount of energy that you use per second or per time, based on time. So, for instance, if you are going up some stairs, it's the same amount of work if you go slowly, very very slowly, or really fast, because you are doing the same work, because force times distance is the same. But you know that something is different. If you go very slow, you are using less power, so you are doing the same work in more time. So the ratio, then you have a bigger number. So a smaller number, less power. So if you use the unit watt as 1 joule per second, then you can get kilowatt as 1000 watts times 1 hour, which is 60 minutes times 60 seconds. Then you can get the unit joule. So this is another common practice that we'll see is commonly used today in our society. So anyway, so what are the units that we can use here? Just to give you an example, we can see here that if I define 1 joule as 1 Newton meter, this is the same as saying 1 kilogram meter square over second square. I have a definition of energy, but for chemists, sometimes it is frequently found that we use the unit calorie based on the amount of energy that is required to increase the temperature of 1 gram of water by 1 degree Celsius. So this is a very common practice, and you have heard the word calorie many times. In fact, you have heard one one calorie in food, which is in this case represented by a capital letter C, 1 kilocalorie of a regular calorie here. So, for instance, if you look at your granola bar, you will find that they have, I don't know, 240 calories. Well, they are really talking about kilocalories. That would be 240,000 calories in our case. And if we want to find a conversion factor between calories and joules here, we just have to look at the energy required in joules to go from a particular temperature 1 degree more if I am talking about 1 gram of water. And that amount of energy comes to be 4.184 joules. So 4.184 joules is equivalent to 1 calorie. So we now have a bridge that allows us to go from one system of units to the other ones. The joules, of course, is the standard SI system of units. The calorie is more a conventional chemical form of doing it, right? And just for those of you who are worried about significant figures, in this case we're using these numbers as exact numbers, so don't worry at all about the significant figures. And finally, just to give you an example of how these energies relate to everyday use, I have here the list of units that we have been talking about, and I mentioned before something like a 100 watt bulb, and here you see the 100 watt as giving you a fairly good idea of what things we are using. You might be thinking about something that has more power. For instance, you might have a small motorcycle will give you something like 50,000 watts of power. You might have a hair dryer. My wife has a hair dryer. Of course, I don't use a hair dryer, but you might have one, and hair dryers are about 1200 watts. So that gives you an idea of everyday things. Now, if you think about the energy that you as a person require for doing things, doing homework and so on, let me give you an idea here. For instance, if you are running about a mile, this depends on the mass of the body and other things, but these are kind of the levels of energy that you are using. Here you have like 100 calories with capital C. This would be 100 food calories. So, for instance, if you are eating a Big Mac, which is probably, I don't know, with the whole supersize and so on, maybe we're talking about 300-400 calories. You will really need to do a lot of running to get rid of those 400 calories. Now, if you compare what happens around the world, and this is something important for environmental studies, is in the U.S., for instance, average U.S. citizen will use this amount of energy. You see, they're really huge. If you think about 10 to the 8, that would be 8 decimal points moved to the right. That's hundreds of billion. It's like a billion or something. More like 100 million joules per day, which is kind of a lot. Anyways, I hope this helped you to see a little bit about the units. Remember, if you have any questions, please call me, email me, text me, and find me any way you like. I hope you have a wonderful day, and I hope you have enjoyed these slides.